Maybe you saw this episode, Easy GPU Programming with Adaptive C++, where I mention a 68 times performance improvement. This was with some very simple offloading of my trivially easy to parallelize game of life simulation that I had written. A lot of you commented that I should have been able to get much faster than 68 times, although I was just using the GPU on my laptop. And it's true, if I had been using a discrete GPU, I would have gotten much faster times than I did, but really not the point. In this video, I comment that GCC consistently produces code that is 2 times faster than Clang. I knew that I could not just let that lie, so I had to come back to it. And I did. I did a lot of research. I've spent approximately the last 4 months trying to get to the bottom of this. Not full-time, of course, but off and on coming back to it. And that's what this episode is going to be all about. This episode is sponsored by JetBrains. Today we need tools that help us work quickly and effectively. CLion is a powerful JetBrains IDE for C and C++ that makes filling this need its main goal, integrating code analysis, refactorings, and a wide range of tools into your day-to-day development. The latest version of CLion introduces deep integrations with the ReSharper C++, Writer C++ language engine, performance improvements for the debugger, new features for embedded development, and enhancements for project models and build tools. Use the code CPPWeeklyCLion to get 25% off when purchasing a new CLion subscription or renewing your existing one. Every version of this that I have tested is in the official Lefticus/CPP_weekly GitHub project in the parallel algorithms folder. The original version is this gameoflife.cpp, and that is the one where I noticed these performance discrepancies between GCC and Clang. It is important to note that this is a little bit of a special case in that it is very little code. The entire thing is 306 lines. That includes the test cases and probably nearly 100 lines of comments as well. So this is a very, very small project. The compiler has complete visibility into it, all of the standard algorithms that I'm using, and it has all the flexibility in the world to inline and optimize to its heart's content. So I ran a few different tests, a lot of times across a bunch of compiler configurations on a system that wasn't really being used for anything else, so that I could fairly well trust the timings that came back, and all of these times are in the tens of seconds. So we're not talking micro benchmark kind of scenario. All of this is available as a Google Sheet that you will have access to in the links in this video description. Now, you can see that I was running this on a VMware host, but that doesn't make any difference for these test cases, or at least not any notable difference when we're talking about the scale of these things. I did O1, O0, O2, O3, OS, and OG with mark native and without specifying the architecture specifically, and with libstd_C++ and libc++ as appropriate for Clang and GCC. I did test multiple versions of Clang and GCC, but the results that I saw were consistent. And it's probably best viewed if you just look at the pivot table here, where you can compare the Clang and GCC results across the different optimization levels in the times run and milliseconds here. Now, this chart gets a bit jumbled together, so I will leave the numbers here on the screen so that you can look at them, and I will tell you some of the conclusions that I came to. The first thing that I'd like to point out, which is just true across every test that I ran, is that with GCC, O1 always produced code that was faster than O0, O2 always produced code that was faster than O1, and O3 always produced code that was faster than O2. Now things were a bit hit and miss and a little weird with OG and OS. And if you care about the file sizes generated from these things, which you might when you look at the difference between GCC's OS and Clang's OS, then just go to the link and check out the raw data yourself. So that was true across the board. Now also true across the board, no matter what, is that O3 produced the fastest code for both GCC and Clang. This is contrary to some things that you may have heard recently. I have seen reports, conference talks, etc., saying that O3 is not worth it because it just bloats the binary and makes your code slower usually, when that's, well, just clearly wrong in this case. And wrong by a pretty wide margin. This is about 2.5 times faster than O2 when we're talking about GCC. And with Clang, O3 is, don't know, 30% faster, something like that, than O2. Another thing that I thought was interesting was in this case, -mark native had only a marginal difference, a couple of percent. Now, if getting every single percentage point possible out of your performance is important to you, then of course run with some sort of native architecture flags. You want all the SSE and all the bit twiddling opcodes and everything else that you're going to get, so just do it. There's no harm there, but as far as looking at the scale of things here, it's not worth discussing for the sake of this comparison. One thing that I absolutely learned, which I'd already had a clue about this, is that if performance is your #1 goal, then you really need to compare all optimization levels on all compilers that you support and pick the combination that actually gives you the best possible performance. This is kind of my point. Let's go ahead and look at the scale of these things. In my initial test cases, GCC's O3 was 42 seconds and Clang's O3 was 98 seconds. And that's just huge. That's a massive difference. And if we look at O0, GCC is still generating code that's almost twice as fast as Clang's O0, which I gotta honestly say just makes absolutely no sense at all. The next things that were true, except for the one outlying case that you have probably already spied here, where we see that we are at 28 seconds for Clang versus 40 seconds for GCC. GCC always beat Clang, except for this one particular test case. Another thing that was very odd here is that GCC's O1 performance was always slightly worse than Clang's O1 performance. I don't know why, but perhaps even more interesting of note is that Clang's O2 performance was almost always worse than Clang's O1 performance. So this is part of my point of that you have to try every single possible combination. If your code does not work at O3, I can almost guarantee it is because you have undefined behavior in your program. Okay, so fine, your code doesn't work at O3, you know you can't trust it, so you're using O2 blindly and assuming that this is going to result in faster code. But there's an actual real chance that it doesn't, that O1 is producing better code for you than even O2 could. All right, we're gonna have to get to this change. What is this one commit that I made that made the code 5 times faster on Clang than it had been with all previous other tests, and now all of a sudden Clang is beating GCC by a wide margin? Let's look at this block of code right here. This is a function. It doesn't need to be const expert because it's not actually being called at compile time. That is simply used to determine the smallest possible integer size that can hold the index values that we care about. So what I wanted to do, as the comment says, is that I wanted to compact my point type. My point has an x and a y coordinate. If I have a grid that is, for example, 100 by 100, then there's no reason not to use int 8t for my index size, because that would make my point type smaller, therefore more things fit in the cache, therefore my code is faster. That is the first point that I need to make here. When I was first looking into this, I thought that I saw some oddities around cout. What I thought was that when I had these cout timer events in here, that Clang was kind of losing its mind and generating much worse code, and this is just based on eyeballing it in Compiler Explorer. So I, first of all, went and removed these couts. And you get to this no IO streams version, and I'm no longer printing the Game of Life board necessarily, or I'm using putcar to do that, and things are considerably simpler than they were. I'm just using puts and putcar, and it's all like very simple code. No IO streams in here at all. Well, that made no difference at all. And then I'm like just pushing around at all kinds of things. I end up on this version, which was just me saying like, okay, fine, maybe GCC is just inlining more code than Clang is, because I'm looking again at Compiler Explorer and I'm seeing all kinds of differences. And I don't know, so I sprinkle always inline everywhere, because these are small functions, they should be inlined anyhow. Well, when I was poking around in here, I also kind of just accidentally made the change of having an int64t in here for my index sizes instead of using that compacted size. And that's when I noticed the huge change in performance was with this set of changes. If I look over here and I see the SHAs here for each of these files, the first one was my baseline. My second one was removing IO streams from the executable, and that made no real difference that we can really note. The third thing that I checked was the one that had size t indexes, so it's larger, so these things are now all bigger and there's theoretically less room in the cache for data, and I had always inline enabled. And this is just nuts. Even on an O0 build, where this should make basically no difference at all, the code is nearly 3 times as fast on Clang, and then Clang is starting to get almost as fast as GCC until we get to this O2 level where Clang starts to blow GCC out of the water. And then the fourth thing that I did was going back and changing the size t index to a minimum sized index again, and proving to myself that that was really the thing that had the main performance hit. Now you can still see the impact of the always inline. So even on a O0 build, we get better performance because of those always inline things. And it makes, you know, a little bit of difference here on GCC as well. But once you start trusting the compiler to make your inlining decisions for you, it basically makes no difference at all until we get again to OG and OS kind of comparisons. Okay, lots of words. Let's get to the final result. I found this random website, diff checker. Don't ask me anything about it at all, but it was a way for me to show you a link that this is the change. I went from using compactly sized indices to using int64t and size t. And that's it. That's the change. That made the code 5 times faster. So let's go ahead and look in Compiler Explorer and see what differences it made so that we can understand what happened. Here is a Compiler Explorer link that you can look at. That is the only difference between these two versions, is the size of the indexes. I probably should have just made that an if-def, but whatever. And I've got my side-by-side comparisons here, editor 1 and editor 2. Those are reversed, but you get the idea. You can scroll through the binary if you want to, and then you can easily observe in the diff view the minor subtle changes that were made between these two binaries. It is literally completely different code. I can't even begin to decipher what Clang did between these two versions when it was doing 8-bit and 16 and 32-bit comparisons compared to doing 64-bit comparisons. It's completely different. It has a bunch of data tables that have been inlined, and confusingly, the one that has all of the inlined data tables and stuff is the one with the smaller indices. So I would think, oh, it has all of this data that it can directly index and it can optimize things. No, it just generated considerably worse wall clock time code. And this is where I am leaving this. It's not a sized and unsigned. Your homework is to figure out what happened. Is this a bug in Clang? I don't know. A missed optimization opportunity? I don't know. Is one generating incorrect code? I don't think so. I'm pretty sure not. I think they're both doing the exact same thing. I don't think that this is a signed and unsigned question. It comes up far too often in conference talks and such, where people say that we have to do signed integer math because it's faster. Now, I don't really think that has anything to do with anything here. This all comes down to the size of the types that are being operated on. So that's your homework. Figure out what's happening. You'll have all the links. Go down to the video description. This is where I'm leaving this, but the takeaways. You've got to compare these things across all compilers if you really care. And we might even have to throw in -OS and -OZ or something. Perhaps you're working on a processor that's very tiny and you have cache, but you don't have a branch predictor, or you have a branch predictor, but your cache is small. I don't know. You just have to compare these things and find out for yourself. And just in general, this seems to be almost completely unpredictable to me. I don't understand how code that should have been less cache friendly because it was larger objects generated code so much faster. Anyhow, I hope you enjoyed this episode of C++ Weekly. A little bit of a mystery here. Let me know what you find, and I look forward to seeing your presentation on what exactly went on here. And I'll catch you in the next episode.